In this video, I'm going to focus on engineering mechanics as it relates to aeronautical engineering for HSC engineering studies. I will briefly talk about job prospects in aeronautical engineering, and then I will talk about controlling flight. I'll talk about generating lift in the aerofoil. I'll talk about Bernoulli's principle, and I'll talk about propulsion. To start off with, in Australia, in New South Wales, if you're going through ADFA or the Defence Force, that's usually partnered with New South Wales, and so New South Wales Uni offers an aviation course. Sydney Uni also offers aeronautical engineering, and Wollongong offers aerospace engineering. It's worth pointing out that Australia, because it has a relatively small aeronautical engineering field, typically you'll need to do a postgraduate course, either a master's or a PhD. There are not a great number of places. Curtin University is the only place I can see that offers PhDs in aeronautical engineering in Australia. I also looked at questions asked by people on Reddit about work as aeronautical engineering, and I think they sort of gave mixed opinions. But I think that's a good place to get. I mean, these are often ones I've saved several years ago. But going onto Reddit and asking about what the prospects look like at the moment in the country that you're in is a good way to understand what the field looks like. Using US stats, these were posted in 2022, but they're from data that's 2 years old, that the average US job growth is 14%, so there's 14% new jobs for every field, that aerospace engineers are shown at about 5%, so there's still growth, it's just not growing as fast relative to the average job growth. Whereas they show biomedical engineers way out in front. Now, I don't know how reliable that is, because when I look at other Bureau of Labor Statistics information, they say that aeronautical engineers typically make more money on average, and that there is a larger section of the economy, so 61,000 versus 19,000. So it's 3 times as many jobs as there are biomedical engineer jobs. I will say that I think both areas are probably growth areas. Aerospace, in terms of dollar values, is supposed to be, when we're talking about aerospace rather than aeronautical, is probably going to be a massive growth area as companies like Amazon and Sky Blue, SpaceX work on monetizing spaceflight. So now that I've talked about that, training the profession and career prospects, technologies unique to the profession, I think are covered very well in this mechanics section. So we're going to look at how we control flight. We're going to look at the Bernoulli effect, and we're going to then look at the fluid dynamics sections of the textbook. So I'll be referring to Copeland's Engineering Studies: A Definitive Guide, Volume 2. There is a newer volume. The Volume 2, there's a newer edition. This is the 3rd edition, and there's now a 4th edition. The 4th edition has the red cover. So mine are older pages. So the first thing is you need to be able to name the key parts of the plane, particularly the parts of the plane that control flight. So we'll go into our notes on that. So previously I showed this video saying the Wright brothers didn't invent flight, and they talked about something called wing warping. They said that the Wright flyer controlled its flight by actually twisting the wings. You can see here we've got these axes. Generally, when talking about, so we have axes in 3D, and generally I think we say the z-axis is up, so we say yaw is rotation around the z-axis, for example. So we'll have a look at these 3 things. So here's a picture of the Wright flyer, and we can see here the elevator, and I think they had a box rudder, but we're going to move on to specifically, so we've got this picture here. It's again labels things. This adds a little bit more than the textbook does. The textbook doesn't talk about slots and slats. It does cover flaps, which is something we're going to talk about later. So back to that. Okay, so we've got ailerons. Ailerons control roll, and roll is the primary way that we change direction with especially large aircraft. The ailerons are way out at the end of the wing. They're not the wing tips, but they're just before the wing tips. They're not to be confused with flaps, which we'll talk about in a second. So aileron comes from the French term for little wing. So the Wright brothers didn't invent ailerons. We talked about how they had used wing warping, but aileron means little wing in French. This is in class. I generally play the song Little Wing by Jimi Hendrix. It's a pretty cool song. My mnemonic to help us remember this is I have a picture of Ron Weasley, and he's driving a flying car with his mate Roll. And you can see that the roll it's a sesame seed roll because they're my favorite rolls. And there's little wings there to help you remember that it's not only does it mean little wing, but the location of the ailerons is on the end of the wings. So probably won't help many people, that mnemonic, but it might help some people. So here we can see that the aileron is located at the end of the wing and it controls roll. Okay, so the next location we're going to look at is the elevators, and the elevators are located on the horizontal stabilizer. And I find that most students have an easier time remembering the terminology horizontal stabilizer, but it's also called the tail. And we can have a look at what they look like in practice. So we can see elevators there, and there, and there. And here I have Amy from Pitch Perfect, and she is in an elevator, and she's holding a tail. So that's to help us remember that elevators control pitch, and they're located on the tail, or the horizontal stabilizer. I also have Vin Diesel's first movie was called Pitch Black. It's a pretty good movie. It's set in Australia. I thought it was good when I saw it in high school, but when I showed it to my daughters, they were unimpressed. And he's got a tail in the background. He's actually got two tails. He's got like the Sonic's mate tails. Because he's a furry. Anyway, so elevators are located on the tail and they control pitch. So like Pitch Perfect or Pitch Black. That's elevators. Okay, so then we have the rudder, and the rudder controls yaw. Yaw is, well, like we said before, rotation around the the z-axis, or the vertical axis. So we can see here the rudder. Another picture of a rudder there. The rudder is the movable part, and we call this the vertical stabilizer. Another term for that is the fin. So here I have a shark. This shark is called yaws, and the fin is what sticks up out of the water, and that shark has an udder, not a rudder, an udder. I didn't make this picture. It was already on the internet. And you know what? There was another picture on the internet that already existed of someone who wanted to make a shark with an udder. Anyway, there you can combine elevators and ailerons. So planes that have delta wings, so like stealth bombers and the Concorde, they have elevons. Probably not going to be in the HSC. I just thought it was worth mentioning. Okay, so we've talked about the ways that we control flight. Next thing we're going to talk about is how do we actually generate lift? How do planes fly? Well, I've got this XKCD comic. It's a pretty good comic. I don't know if it's still going. I haven't read it in years and years. But this one from 20 years ago, time of recording, it talked about airfoils. And it has a question about how do planes fly. Well, what it says here is that the air going over the top of the wing is traveling faster than the air below. Faster air exerts less pressure, so the wing is lifted upwards. And it says, but then why can planes fly down? And then we have different ways of responding to this question. Good, bad, and very bad. Now, the interesting thing about this webcomic is that they always have extra bits that, I didn't know about that. I'd read like 1,000 of these before, 1,000 maybe, before I realized and went back and read them all again. And what's interesting is that they give pretty good descriptions of why the joke works. So, because a lot of them are based on maths and engineering. So, we've got this fundamental idea. Let's have a look at how that works. So specifically to talk about how that works, to answer that question, planes can fly upside down. And the main reason is because this angle of attack is what matters. The angle of the wing is probably more important than the shape of the wing itself. And as long as the shape of the wing is the same, as long as we get this constricted area here, we're going to have faster air moving over the top. And that's why in the movie Top Gun, we have the international diplomacy where he flies upside down. And I'll pause before he gives the guy the finger. Oh, too slow. Anyway, okay, so what is going on here? Well, the first thing we can look at is we've got a very old video, but it's got a great... I'm not going to play the audio because I think I've learned my lesson about playing audio on recordings. But we can see that as we increase the angle of the wing, we're going to start generating more and more lift. The air above is going to go faster and faster. But while we do that, we can also see this cloudy area here that we call turbulent flow. And this turbulence above the wing, it is not generating lift. So if we lift too high, we're going to generate too much lift. So that's where we want. We can see there the rounded shape is going to help produce less turbulence for the same angle. But we do have problems when we start getting too high. When the angle gets too high, we're going to have to come back to this and talk about how we're going to deal with this in a second. So, I have lots and lots and lots of videos that talk about how planes generate lift. They're all okay, but I say that really you don't want to focus on these unless you really want additional content. I try not to overwhelm people with too much content, so I'm instead going to stick with this one. I really like Brady Haran. He has a good podcast, and he has lots of web channels where he talks about science. His physics one is called 60 Symbols, and in this one, he talks about the 3 reasons that wings generate lift. So it's not just about the air going faster. As a matter of fact, he interviews, and we can see a plane going upside down. I'll see if I can remember my spot where I'm up to. He talks about the air going upside down, but first of all, so he always interviews professors and things.
Fundamental one.
Oh. Okay, so the fundamental concept is that the air below has a higher pressure than the air above, and that we know that high pressure pushes and low pressure sucks. And so the argument is that the air above is going a longer distance. That's the argument. The air above is going a longer distance, and if it's going a longer distance, it's going to be more spread out. And if it's going to be more spread out, it's going to have lower pressure. That's the general understanding. Turns out that's actually wrong, because as a matter of fact, the air above the wing is actually going faster than you would expect. So there's no reason for it to catch up. But as long as it's going faster, it follows the rule that what we're going to learn about in a second, with Bernoulli's principle, that because it's going faster, it's going to have a lower pressure. And so then, as we go further on, he then talks about how this still works even if you're upside down. And what he says is that because of the angle of attack, we're going to have this compression here. Now, he does talk about how that would make sense if there was some sort of blockage, but there's no blockage. But even then, it still works. And because of that constriction, because that's constricted, it's going to go faster. That's something to do with called the Venturi Effect. And because it's going faster, it has a lower pressure. Also, that a consideration talks about is because here the air is going straight and now it's going down. So if that air is going down, well, there has to be something to balance out the air being moved down. If the air is being moved down, something has to move up, and the wing is going to move up. He also talks about, I don't know, I couldn't find exactly where on this video, but he talks about that there's just simply more air hitting the bottom of the wing than hitting the top of the wing. So there are different explanations. So I've come up with this way of helping us to remember it. Now, the idea here is that you can have one explanation or two explanations or four explanations, but you want to start from the top and work your way down. You don't want to just write, if you just write conservation, mass, momentum, and energy cause the wing to generate lift. If you write that and you only write that, there's a risk that the marker, that HSC marker, might not give you full marks for that. So let's start from the top, and we're just going to add a new sentence to make our explanation better and better. So first of all, we can say, the wing generates lift because the air above has lower pressure than the air below, and that pushes it up. Right? That's really easy, right? We know that there's low pressure above the wing, high pressure below the. low pressure above the wing, high pressure below the wing. We know that low pressure sucks, high pressure blows. That combination of sucking and blowing lifts the wing into the air. Okay, then we have this thing called Bernoulli's principle, which means that the air above is going faster. Now, we haven't explored that yet, but the air above the wing is going faster, and we've said that faster air has lower pressure. And then we're going to add to that, we're going to say the angle of the wing means that more air hits the bottom of the wing, which pushes it up. Now, generally, we don't focus on that too much, just because this Bernoulli's principle component is such a noteworthy consideration. We tend to focus on that. And then lastly, the most, like as a capstone, you can add on a sentence that says, this conserves mass, momentum, and energy, which causes the wing to generate lift. And if you watch this video, that's a 10-minute description on how exactly we're conserving mass, momentum, and energy. Okay, so the next thing we're going to talk about is we said if we go too high, we're going to start getting turbulence on the back of the wing, and that's going to mean that we're not generating lift. When we stop generating lift, the term that we use for that is stalling. It has nothing to do with the engine stalling, but that means that the wing is no longer lifting the plane into the air. And when you start to have stalling, the plane starts falling, or it falls out of the sky like a brick, and that is bad. There have been a number of high-profile plane crashes that have been found because the pilots didn't respond to wing stall. There's an optimal, if you're trying to generate lift, if you're trying to gain altitude, there is an optimum angle, which is different for every plane based on its drag profile. But typically, a wing can still generate lift even if it's pointed downwards at -8 degrees. And we can see here at 12 degrees, it's generating a good amount of lift. And then at 19 degrees, this wing is starting to generate we've drawn here the turbulence on the back of the wing, and that is now it's no longer generating lift and is now going to fall. This is a more detailed answer, which it talks about the flight envelope. And the idea is that as we increase the angle of attack, we're going to continue to generate more drag. And eventually we're going to generate more drag than we're generating lift, and the plane is going to start to fall. So we want to try and keep the angle of attack below that critical angle where it will no longer generate lift and start to stall. Now, if I had more time, I would show videos of stalling. Actually, a student gave me a really good video of stall training just recently, but I'm not going to show that now because I don't have it ready. And here we can see the coefficient of lift based on the angle of attack, and we can see on this plane, yeah, it drops off at something like 19 degrees. Okay, so I said right at the beginning that when we were looking at the flight surfaces, that there was something at the front of the wing called slats and slots. This is one of my first pictures I made for school, and I wanted students to be able to remember what's the difference between slots and slats. So slot machines don't move, whereas Michael Slater, the cricket commentator, he can move. And that helps me to remember that slots tend to be fixed in location, whereas slats, they can move to generate more lift without prevent wing stalling. So here we can see that with the slot or with the slat, we still continue to get this lamellar flow over the wing generating lift, whereas if we had that same angle without a slot or a slat, we would get the turbulence on the back of the wing and we wouldn't be generating lift and we'd have a wing stall. I should also point out that this picture doesn't condone gambling or Michael Slater. My mum says that gambling's a mug's game. Okay, so now we can go back to this video from 1938, and we can see that we've got the turbulence here. So this wing, if it was a real, attached to a plane, would probably be starting to fall. And what we can do to prevent that is we can put a flap, and the flap is like a slot and a slat, except it just goes on the back. And it makes it we're able to have a larger angle attack, generate more lift without creating stalling, especially at lower speeds. And they're going to show some more slats, and then I think we've got slots here as well in this video. Oh no, just move a little flap. We can see we're actually getting some of the leading edge slot. Okay, so we've got a leading edge slot, and that is going to allow us to now that's actually moving, so we would call that a slat, but that's because it's an experiment. Okay, So here we have a video as well on how do flaps work on aircraft. We can see that modern aircraft, especially big commercial aircraft like 747s and larger, or 737s and larger, that they have multi-stage slots, multi-part flaps, which just allow to increase as much lift as possible. So we've now talked about how the wing generates lift. We're now going to look at this Bernoulli's principle. So Bernoulli's principle, if I summarize Wikipedia, I didn't want that, I want this. Bernoulli's principle says that as speed of the fluid increases, pressure decreases. So in this case, the fluid that we're talking about is air. We don't often think of gases as being fluids, but no, from an engineering perspective, we consider air to be a fluid, and as the speed of the air increases, pressure decreases. So we said that the air above the wing is going faster, which means it's going to have lower pressure. Low pressure is a decrease in pressure. Okay, so we've understood now what Bernoulli's principle is, and Venturi built on the Bernoulli principle, and he came up with the Venturi effect. And what he said is that if you have a pipe, or if you have a contraction of a fluid, then you're going to increase the speed of the fluid, and by increasing the speed of the fluid, we're going to decrease the pressure. So let's have a look at the classic example of that. Is if you have a hose, and I think actually one of these videos does even. I have several videos on Bernoulli's principle, but on one of these, I don't want to click around because I don't want to take a risk. But if you just cover a hose with your I'll pause. Okay, so I found this video where someone is demonstrating with a hose that when we cover half of the hose, the same amount of mass of water has to get through the hose. And what will happen is that the water will now travel faster in order to allow to conserve the flow rate of water, to ensure that the same mass of water is passing through the hose. Now, there were a couple of other videos. So this person here, this guy here, he was like a really famous, Julius Miller. He was like a famous Australian science teacher before my time. But anyway, there's this equation. We don't need to worry about the equation as far as I'm concerned for the HSC. I don't write the HSC, so I don't know. But I think it'd be very unlikely based on past HSCs, and it won't be in any test I write. Now, this experiment here is a good way of demonstrating Bernoulli's principle. So, with a Venturi tube. So here we have a tube that narrows, and we've said that if it narrows, it's going to go faster. And if it goes faster, then that means it's going to have lower pressure. Lower pressure, we said, is the same as suction. So that's why this red liquid is being sucked up, whereas this wider tube has high pressure and therefore is pushing the water down. So if we see that before the experiment is conducted, or actually just press play, we can see that when the air is turned off, the water returns to be equal because the pressure is equal in all three locations. Okay, so we can look more into that if you want by going to Khan Academy, which has lessons on Bernoulli's principle and fluid dynamics. But we're going to focus specifically on the Pitot Tube. And the Pitot Tube is, well, you can see that big aircraft, anything bigger than a 737, has lots of Pitot Tubes. And before, when I mentioned the, so the Air France flights, I want to say 448 or something like that, that crashed in the Atlantic Ocean. And I think it was in the Caribbean, but it crashed because the Pitot Tube had got frosted over, I believe. I could be wrong. That's what caused it to stall, and then they didn't respond to the stall appropriately. And there's a good 99% Invisible episode, which I didn't look up beforehand, but I will look it up. It's called Children of the Magenta. And in this episode, they talk about how reliance, 447, it's pretty close, how reliance on the autopilot is possibly a big factor in why this plane crashed. And as a result, the follow-on from that was that after this, pilots had to fly manually for some part of long-haul flights. So worth mentioning that now. But so here we can see a Pitot tube and more pictures of Pitot tubes. And the idea of the Pitot tube, if we go to this picture, while it's loading. So the idea is here that we're comparing the pressure of two different airs. We're comparing the static air pressure from just the side of the plane, and we're comparing the air that the plane is flying directly into. And as you can imagine, that when the plane's stationary, those two air, the speed of those two air, and therefore the pressure of that air moving into the Pitot tube, is going to be the same. But as the plane starts going faster, there's going to be faster air being forced into the Pitot tube, this V, relative to these the pressure from the side. So the PT is going to be greater than PS. And as as the plane goes faster and faster, that dynamic pressure, the air coming through the Pitot tube, is going to increase proportional to the static pressure, and we can measure that. We used to be able to measure that mechanically. These days we measure it electronically. We measure that pressure, and we can convert that pressure to a speed. So that's the principle of a Pitot tube. The other application of a Pitot tube is I should have had... Oh, here we go. This bag of chips. Sorry, not a Pitot tube. So we're also going to look at altimeters. So the altimeter is based on the idea that as we go higher... So just start off by saying, so this bag of chips, it started off 1,000 meters off sea level, and it was already pretty puffy at that point because it was probably packaged close to sea level. And as this person is driving higher and higher up, the bag is... The pressure inside the bag is not increasing. The pressure inside the bag is not increasing. But what is happening is that the air in the car is losing pressure. As the person is driving up, the air pressure is getting thinner and thinner and thinner until eventually at the top of the hill, eventually at 3,500 meters, the air pressure is high enough that the bag pops. Well, if we can measure pressure on the bag, then what we can do is we can use that to determine the altitude. And this is, I think, similar to how a barometer works. Now, I'm on my... Oh, no, we're going to go into propulsion. But what I'm going to do before I move on further is I'm now going to go back to the book and we'll cover those concepts again. So we know that we should be able to label all these parts of the plane. We're particularly interested in the flight surfaces, the aileron, the elevator, and the rudder. And it's worth noting we should be able to describe the flap's role in preventing wing stall. Now, in terms of forces on a plane, there are four forces that we are concerned with. We have lift generated from the wing, and that is always perpendicular to the angle of the wing, perpendicular to the angle of attack. We have weight, and weight is always down. It's the definition of down. It always falls vertically towards the center of the earth. We have drag and thrust, and drag and thrust will oppose each other. They will always be equal to the angle of attack. So whatever the angle of attack is, that will be the same angle for thrust and drag. They're going to be collinear forces. Now, in level flight, we know that the lift is going to equal the weight because we're not climbing, and we're going to say that the thrust is going to be equal to the drag. I'm not too interested in that, but it's worth just quickly mentioning that here. When we talked about couples in year 11, I talked about how the role of the tail, which is where it's LT for tail, is important in preventing a moment couple, or it's providing that third force in order to stop an uncontrolled rotation of the center of mass and the lift generated from the wing. Now, in a steady climb, I don't really go into these forces. I used to when I first started teaching, but I find that they're not worth spending a lot of time on in class because we don't discuss it. There tends not to be many marks in it, and by all means, I think that good students should be reading this and really making sure they understand it. But for students who are struggling to understand trusses, this is probably something that you can afford to ignore. Now, what I will say is that we can use the angle of attack to determine, say, how far a plane can glide, or a glider can glide. We've talked about basics of aerodynamics. So the classical theory is just relying on Bernoulli's principle, whereas the second theory is the lift from turning flow. So we've already talked about how there's multiple components to generating lift, and I'm not going to go into that in any more detail here. We've talked about stalling. We've talked about how if we increase the angle of attack too high, we're going to get turbulent airflow. And a way of dealing with that is by having slots, slats, and flaps. Now, a big part of this course is we're going to spend a lot of time, and I will go through some examples. I always go through examples on the board, but I haven't recorded them yet. I will try to soon. Calculating the lift to drag ratio using force polygons. So my way of approaching this is by saying that because the thrust and drag are collinear, that means we can put those two forces together and we can make a force triangle, which a vector triangle is pretty easy to work with. We know that weight has to always be the hypotenuse and weight always has to be down. So if you remember that, I find that that gives you a really good start to say, well, okay, I'm going to draw a triangle. I know the angle of attack. Now, if I was told the angle of attack is 15, that means this angle is 15. Now, you can prove that with geometry, but for me, I just accept that if the angle of attack is 15, the angle of my triangle here is going to be 15. I know that weight is going to be my hypotenuse, and then I can use trigonometry to find my lift and my thrust minus drag. If I don't have any thrust, it'll just be the value of the drag, say for instance with a glider. Okay, so we've talked about Bernoulli's principle. Now, I said that we don't need to worry about this. I will not ever ask you about this formula. It's there, but I'm not going to expect you to learn that formula. We've talked about the Venturi effect, and what we've said there is that because area 2 is smaller than area 1, V2 must be larger than V1. Is what we're looking at there. Okay, so then we have questions on bending stress in airframes. There have been questions on this. Students should expect there to be, this is a good opportunity to ask questions about cantilevers. I have heard some teachers talk about how this maybe isn't the most appropriate place to talk about bending because of the fact that it's kind of abstracted, but everything we do in high school is abstracted. So the fact is we should be prepared for these sorts of questions. Then we're going to go finally to propulsion systems. So I'll go through here and then I'll go through my links and sources later. So first of all, we've got piston engine. So from the Wright brothers, they built a piston engine out of aluminium because aluminium was very light, and they painted it black to not give people any information as to what material they were using. And that was still used right up till World War II. At the end of World War II, as we've already discussed in our other video, the Germans and the English both developed jet engines. So they were turbojets, and turbojets have 4 stages of combustion, the same as a petrol engine, except that with a petrol engine, each stroke is done by each piston one at a time. So there's suck, squeeze, bang, blow. So there's intake, compression, combustion, exhaust. In a turbojet, and the analogy that in the video Modern Marvels, they say that the analogy is making one cookie and putting it in the oven, and then mixing up the batter and then putting on the tray and putting in the oven and then taking out of the oven. Whereas a turbojet is like having a conveyor belt of cookies, that the intake is constantly happening. There's constant intake, there's constant compression, there's constant combustion, and then there's constant exhaust. Okay, but it can be summarized as suck, squeeze, bang, blow. The idea is that if you can push the air out of the back of the plane faster than the air going into the plane, you're going to generate thrust. Okay, so then we have an advancement on the turbojet is the turboprop. Now, there's 3 stages. There's 3 developments in turbojets. And I like to think of this as like Pokemon. But the thing is, the Pokemon sound less cool with every evolution. So the turbojet evolves into turboprop. And the turboprop is the same as a turbojet, except it has a propeller on the front. The compressor is used to drive the propeller, and that generates more thrust. Then the next evolution is a turbofan, and a turbo, specifically if we're talking about bypass turbofans, what we're going to have is our fan in the front, right? So let's have a look at our pictures. So we've got our turbojet where we have our intake, it's compressed, we have combustion at the fuel injector, and then it's pushed out at the exhaust. The turbine, the movement of the air through the turbine is what powers the compressor. Then we have the turboprop. It's the same concept, except we have a propeller in the front, and when the air moves through the turbine, now it powers the compressor and the propeller is what generates most of the thrust. Finally, we have the turbofan, and in the turbofan, it's the same concept. The air moves through the intake, comes through the compressor. The combustion happens at the fuel injector, and then it's exhausted out of the turbine. The air passing through the turbine powers the fan and the compressor, but most of the air is pushed through the bypass. And this bypass has two main properties. One, it's more efficient than a turboprop, and two, it's much quieter than a turboprop. These are normally very, very large. So now I'm going to jump back to my propulsion. So we have already talked about Mr. Weiss, Graham Weiss, and he has several videos about aeronautical engineering, way more views than me, so good work. And I encourage any student who wants to really get the best out of engineering studies to watch those videos. So here I have my evolution of my 3 Pokemon. One day I'm going to draw like good quality Pokemon, commission someone on Fiverr to draw some Pokemon for me. But I've got Turbojet, who evolves into Turboprop, and then finally our most recent evolution is Turbofan. Turbofan! Okay, so when we look at the comparison of these, we can see that if we have Turbojet, that turbojets can go at very fast speeds, but they're not very efficient. And then we have turboprops, which are more efficient at low speeds, but then their efficiency really drops down. This is in miles per hour. Unfortunately, not much I can do about that. And then we can see high bypass and low bypass turbofans. So high bypass should be more efficient. They're more efficient. Yes, this is more efficient at a lower speed. So if we're going at 700 k's an hour, the high bypass is going to be like 85% efficient, and the low bypass is going to be 82% efficient, something like that. Okay, it's worth noting that typically high bypass turbofans, so when we take a 747 commercial flight overseas, we're typically going to travel at under the speed of sound. That's where we're going to be efficient, but generally they like to have some room with it, because it gets more and more expensive as they increase their speed. They do want to try and stay below the Mach 1 level, but they want to say subsonic. Okay, so I can't show this entire video, but this video is amazing. And what we're going to look at here is how jet engines work. So they have these anthropomorphized air particles, and they've heard... Just another narrow... There's a plane arriving, a narrow-body aircraft, and they're being shook up by the plane approaching, and they're like, what happened? And they're like, well, let's slow it down. Okay, so it flies past, and they fly through the turbofan. What happened? Well, okay, we're going to find out. Okay, so the air is broken up into 2 parts, right? General souls through the bypass, extreme sports freaks through the compressor. Okay, so we can see the carbon fiber of the fans. So the shape of the fan actually generates lift, but instead of being lift, it's lift in a horizontal direction, so we call that thrust. So the same principle, the Bernoulli's principle, also is the same idea of the aerofoil is also what's happening in a propeller, and that's also what's sucking the air through. Without thrust, we can't generate lift on a fixed-wing aircraft. Okay, so the extreme sport freaks are going through the compressor, and they're starting to get compressed together. They've gone from being blue to yellow as they get squashed together. And they're heating up as they're getting ready for combustion. Okay, so they're all squashed together, they've been compressed, And now kerosene, which is the principal component of jet fuel, is going to be added at a well, in this case, they talk about how there's a lower ratio than typical because bypass engines are more efficient. And so the fuel is injected before it gets to the combustion in this particular turbofan. Okay, so the combustion happens. It's a big party, pretty exciting. And then they get pushed through the turbines. The turbines are what power the fan and the compressor. Now, the bypass is responsible for 90% of the thrust. The general sols who are being sucked through the fan, and then like the extreme sports freak is like, he's dissing the bypass guy, and then the guy who's leading the way, he's like, no, we need both of us. Without the primary flow, you can't get the bypass. Without the bypass, we don't generate enough thrust. So the secondary flow through the bypass is pretty important. Anyway, so it's a pretty great video. It's worth pointing out that these things are enormous. Because we tend to see, it's hard to have a good sense of scale when we look at pictures of planes. So we see pictures of planes and we don't appreciate how big everything is on a 747 or an A380. And to give you a sense of scale, I took this photo when I was at the airport once, and you can see this person walking past, and you can see that a turbofan is substantially larger than a person, and that people can get sucked into them. There's a movie called Donnie Darko, and in Donnie Darko he gets a turbofan, drops on his house. Just trying to get a sense of scale. Yeah, it's pretty big, right? It leaves a lot of damage when it's compared to something like a house. It's pretty. It's easier to appreciate just how big they are. Okay, so the really a thing that's worth considering is that turbofans are quite dangerous. That people do actually get sucked into. Turbofans. Okay, so here we have a question. I don't know what year it's from, unfortunately, but it says, so we've got turboprop engine, and it describes the operation of turboprop engine to produce thrust. So what we would want to talk about there is, I guess they're really looking at, rather than talking about just a piston engine, right? They want you to identify that a turboprop is still a jet engine, and they want you to know that air is moving through a compressor and then being combusted. It's then going through a turbine. The turbine powers the propeller. The propeller generates thrust. Now, I know that sounds like a lot for 2 marks, but you could probably do a smaller variant of that. Okay, and here we have this question here compares business aircraft, which is clearly a jet aircraft, compared to a recreational aircraft, which has propellers. So it's a piston-driven aircraft. I don't think they specify, but and I've had students who in the past have said that maybe it's a turboprop recreational aircraft. I don't take marks off for that, but you really should be comparing to a piston aircraft and making a difference between piston aircraft. So piston aircraft need shorter runways. They operate better at low altitudes, and they're much easier to maintain. They have a lower purchase price as well. So they're considerations for why piston aircraft is still being used, whereas jet aircraft are much faster and they're more efficient. So that's where, and probably quieter too. Depends. Actually, I take that back. Jet aircraft is much louder than propellers, but bypass turbofans are maybe quieter than propellers. I'm not sure. I will say that it's probably worth mentioning that bypass turbofans are much, much, much quieter than turboprops. Turboprops are very loud. I've only been on a turboprop aircraft a couple of times when I was flying into a mine, when I was flying between Latvia and Estonia. And for me, I associate the sound of with crashing because movies have trained me for that. So I thought the plane was going to crash the entire time. That's just what turboprops sound like. And if you're not used to it, it's a bit off-putting because they are really quite loud. Okay, so I have lots of alternative propulsion, and we've looked at some of this in the last video where we looked at innovations that are up and coming. So electric planes, solar planes, fossil fuel propulsion, fossil fuel free jet propulsion. They're all things worth considering, but we'll just quickly go back to the book and check that okay, so there's ramjets and scramjets. So if we want to go at speeds substantially faster than Mach 1, we're not going to need ramjets. And if we're going and faster still, so rockets, they will use scramjets. So I was at a party once and I met someone who was working on scramjets, and she said that it was really interesting that when you spend all of this time building this engine, and then scramjets actually melt in their operation because they travel at such they're traveling at such high speeds. So I thought that was really interesting. I didn't know that prior to that. Okay, so they've gone to fluid mechanics. And we've already covered this idea of Pascal's principle. In terms of hydrostatic pressure, we've talked about how there's one question in 2010 on hydrostatic pressure. I don't think that you need to worry too much about hydrostatic pressure. If you think that you're someone who needs to worry about that, by all means, let me know. We've talked about the Pitot Tube. So here we can see that the air coming in through, what do they label PT as? So I guess it's the pressure from the tube versus the static pressure. We compare those two pressures, and we can set that up to an apparatus to determine the airspeed. And so that's why we use P2 tubes for the airspeed indicator. I don't think I said that up until now. And then lastly, we have the altimeter, and that is used to determine how high we are from above the ground or above sea level. And we use that by having, let's see, a small expandable vessel of air called an aneroid surrounded by static air pressure. As the aircraft ascends, the static air pressure falls, which allows the aneroid to expand. This expansion acts on a linkage system, just like what we have above, and which controls the needles on the altimeter. These days, of course, though, rather than having a linkage system, it's more likely to be a pressure-sensitive resistor or something like that. Okay, and that's everything for mechanics. We're done.